Thank you, Andrea. So first, let me thank the organizers for inviting me. It's great coming here to sunny Marseille. And then let me present my collaborators. So this is a joint work with the group of Mats Larsson, with Daniel Elversson and Carl Larsson, and then with Peter Hansbo. And this talk has two parts. So those are the collaborators in the first part, and then with Alexandre Erne and Guillaume Delay in the second part. And I will speak about combining cut element methods and hybridization in two different contexts. So first of all, cut finite element methods we've been working on for some time now. And typically, in our mind, we've been thinking of level set geometries. So we have some simple, relatively simple interface that can do different things, that can evolve, or that we can have topology change, but it is still one or a few interfaces in contrast to what we see here. So this is a microscope image of a cut through sandstone. And you see here you have much more interfaces. And recently we've been looking at how to compute flow in fractal porous media. And we've been using techniques from this that we developed here, but then it becomes obvious that it's useful to have also degrees of freedom on the actual fractures if you have more complex transmission laws. So then we thought that we'd stay with this framework and we'll try to do hybridization as a means typically to have some polygonal grains and to be able to introduce more complex physics. So that's the first part. And then I would like to contrast this with work on a hybrid high order method with cut cells. So this is typically a low order method, typically an H method, where we use hybridization in combination with cut finite element methods. And this is a high order method designed for polyhedral elements, but where will you introduce cuts to be able to model interfaces through these elements. So I thought that it could be interesting to pit these two ideas against each other in one talk. So let's go back to the beginning. What did we want to do? We wanted, in the origin of unfitted finite element methods, the idea is to solve PDEs on meshes that are not fitted in the domain. So here you have a cube domain plunged into a cube mesh, and this is not fitted. Can you solve a PDE in here? And this is now a trace mesh of a surface plunged into a structured mesh. Can you solve a PD on this surface, a Laplace-Beltrami type equation? And these two situations, I think we have pretty good grasp on now. And so this is, of course, it's an old problem following work by Nitsche, 71, and then Babushka. There is a very large literature on fictitious domain methods, and so to cite some, we have Giraud, Glowinski, Angot, Bertoluzza, and co-workers, and Haslinger Renard. And then, in parallel, unfitted finite element methods were developed in the work, for instance, by Barrett and Elliott, drawing on the work by Babushka, and then Hansbo and Hansbo drawing on the work by Nitsche. And the trace finite element case was introduced and analyzed by Olshansky and Royskin and Grande in 2009. So these two are like the basic workhorses here. So let's see what's going on. We look at Poisson's equation in some domain, and I will now say how are we going to construct our finite element mesh and space on this domain? Well, we plunge it in some box that we can mesh easily. So now we can have the simplest possible mesh, and then we select the elements that intersect the physical boundary, the physical domain, and then we select those that intersect the physical boundary. So we have now all the elements that intersect the physical domain, and then we select the ones that are intersected by the boundary. And you see here I marked the faces associated to these boundary elements in red, because they will play a role. But essentially, it is these elements that are important. And why are they important? Well, of course, you see, if you have some physical phenomenon that goes on in here, and you have an element like this, and you just discretize now, you see, this element here will have a very little piece of the action. So something is likely to go wrong here. Okay, so this first part is just in words what we saw in pictures, but this point here is then the finite element space of order P that we define on this global mesh. And then I get another finite element space by restricting this to this mesh TH of elements that are intersected by the physical domain. So we have some assumptions here that some sufficient conditions on gamma. Let's say that it's smooth, or it can be a polygon with curved boundaries. And it's well resolved by the mesh in the sense that typically any cut is divided in two, and that both parts include a part of the triangle boundary. So what is the method? Well, we can write it on this canonical form, where this capital A now combines the PD on discrete form here and the stabilization term. And the PD on discrete form will be the Nitsche form of the weak formulation. So this is the classical Nitsche form. But you see, it is now defined not on the boundaries of the elements, but this guy cuts through elements. And the right-hand side is also standard. So this is this part here. If you take away the S, this is just Nitsche's method imposing boundary conditions inside the elements. And this is not okay, because if you recall Nitsche's method for the analysis, it requires a trace inequality. And if you cut the elements in an arbitrary fashion, this trace inequality is not robust with respect to the cut. Because we need to take it into the domain, because that's where we have the coercivity. If you look, this A form only controls the H1 norm on omega, which is the physical domain. And the trace inequality is not robust if we only take it into the physical domain. So we need to take it over the whole element. So I want to take the H1 norm of UH on this mesh of all elements that are intersecting the physical domain. And then this is, of course, the idea is that this is, of course, bounded by H1 norm. One part of this is the H1 norm of the physical domain. And then if we add this stabilization operator, we will get the rest. That's the idea of S. The S is there to improve the stability so that we control the H1 norm over the whole mesh domain. And then this is controlled by this, because here we can take the trace inequalities that we need for Nitsche's method over the whole elements, and that is included in the left-hand side. So this is the role of S. And it also must have some weak consistency, so it vanishes as quickly as you like then to get optimal convergence order. And these are the two design criteria. So if you can cook up an S that satisfies this, then you will be fine. And one possibility here is to have a penalty on the derivative jumps over the faces in this interface zone. So this is, of course, for piecewise linears, this is okay. For piecewise quadratics, you need another term. But then, of course, you need a lot of terms if you go to higher order polynomials. But there is a zoo of different such ghost penalty terms that have been cooked up now, both in the case of cat-fem, so for the fictitious domain case, or for the case of trace-fem, where you discretize a PD on the surface. So there's work by Lehrenfeld, and Mats has some work also. So there are some different ideas how to do this. And then, once we have this stability, then we can just proceed essentially as a standard finite element analysis here. We introduce an energy norm We get coercivity in this energy norm. We get continuity for sufficiently smooth solutions here. I'm not very precise here with the regularity. I'm just saying that I have as much regularity as I need to get my convergence order. We need some interpolation estimate on this. We need a stable extension, and then we need the interpolation on that stable extension. So we get this optimal a priori estimate. But if you don't like this, all this regularity that I assume, we also have a result that says that if we modify this argument and we are careful and we introduce some weighting functions to treat these flux terms on the boundary, we can actually get convergence order for regularities down to H1 plus epsilon. So this is robust for low regularity solutions. Thanks to this ghost penalty term, we can also get an estimate of the stiffness matrix condition number that is the same as a finite element method. So you see, the nice thing is that we have a fictitious domain method, but these main characteristics of the methods are the same as a fitted method. Okay, there is no geometry approximation in here, but this you can do, also it can be included. So this is now, I think, a tried and tested method also for more advanced problems. So here we have Stokes flow in an MRI scanned geometry, and this is from shape optimization, and we can see, okay, so this doesn't work, let's see. I'm sorry, I will just change this. I should have been here. So, sorry about that. Now, let's see, this should work. Okay, so this is now bubbles rising in a Newtonian flow and in a non-Newtonian flow. And this interface is now modeled using this CAT-FEM technique, but then in a multi-domain setting. So if we run this, you see that these bubbles start to rise. And you see that now things are happening that are different. So you see that this is getting flatter here, and this is developing this cusp here. So you capture this different physics of multi-phase Newtonian flow and multi-phase non-Newtonian flow. So this is, of course, a complicated problem because you have different constitutive laws. And this is now another shape optimization case. So you can do this in 3D using CAT-FEM. And you see you get a sequence now of different meshes where you can compute. And so this is all the time then in this, plunged in this global mesh. Okay, so let's go on and see if we can combine this with hybridization. So why did we want to do this? Well, now we started to have geometries like this, where we had different domains that you can think of as different grains in a porous medium. And typically, there are things that go on here, like we have strongly varying diffusion between cells, but you can also have strongly varying diffusion within a cell. You can have inclusions here, and we can also have coupled PDs on bulk and surfaces. And we've done, now I showed you the fictitious domain part before, but we also have work on how to discretize PDs on surfaces in a robust way using the similar technique. So it seems like a reasonable idea to combine these two into a framework where you can compute both in the bulk and on these surfaces. So we have work on that, and this will not be included in this talk because it would be too much. But the important idea is then to introduce degrees of freedom or unknowns also on the skeleton, and we then come to this situation where we hybridize. And of course, hybridization then allows for the elimination of the bulk degrees of freedom through static condensation. And you see that, and the idea is to stay true to the framework in the sense that we will have a bulk mesh, and you work with only one structured mesh, and all these quantities will be discretized on meshes extracted from this structured mesh. I'll show you in just a slide. But there is also no requirement for the meshes to match if you don't want to. So this is very flexible, but so I'll focus on one particular case. and then I'll give you one numerical example showing another possibility. So what do? Well, we go back to what we knew from the fictitious domain. We take each of these guys, we plunge them into our global structured mesh. We extract the active cells, the cells that intersect the domain. And similarly, for the skeleton, for the trace, we plunge it into the same mesh and we extract the bulk mesh that is intersected by the trace. So now we have two parts, and of course we do this for every component, and we define finite element spaces in a similar fashion as we did before on these different parts. So we define finite element space here, a finite element space here, and they are all the same. And then we proceed by restriction so that we have something on the trace. And we define a global mesh, which is now the sum of the skeleton meshes, and or the skeleton mesh and the skeleton meshes and these bulk meshes. Now we introduce a model problem. So let's look at the Poisson interface problem. It'll come back again later. So this is our workhorse. This is the simplest version. So the jump of the fluxes is 0. The jump of u is 0. To proceed now, I will have the same weak formulation. UH is in this composite space, and I look for it for all V in the same composite space. But what is A here? Well, A is the sum over all the bulk domains. And if you look at this here, we extract this guy. Let's see, actually everything, if I extract everything that is within this parenthesis, that's exactly the fictitious domain discretization on one domain that we had on in the first part. Just that these jumps will connect not to data, but they will connect to the skeleton variable. And this guy is now an additional penalty term that will stabilize this skeletal variable. So this is a hybridized Nitsche formulation drawing from the fictitious domain method. This is a ghost penalty stabilizing the trace variable, drawing from what we know from discretizing, for instance, Laplace-Beltramian surfaces. So this, and if you have in the fitted case, this is coincides with the hybridized Nitsche method proposed by Egger in 2009. So what about stabilization for these guys now? Well, in the bulk, we'll do exactly as we did the fictitious domain case, so we don't need to go back to that. But here, we need to do something else. And here, so here there's, for the traces, there is now also a zoo of different stabilizing operators. So we chose here to use this variant introduced by Larsen and Zahidi, which stabilizes the jumps between the elements, but also the normal derivatives from this, from the trace. So together these will ensure coercivity of this guy on the bulk mesh domain. But there, as I said, here there are several different variants, also depending, of course, of the order. But there is another one that essentially only uses the normal stabilization, but extending it into the bulk that was proposed in parallel by us and by Lehrenfeld and Royskin in two different works. Anyway, we go back, we get a similar energy norm, and we get the following energy estimate. So this is similar to the fictitious domain case. We have this convergence of the bulk of the bulk part, but you can also, that was selected to take out the convergence of the trace part here. And you see that since these can be separated, you can, if you want to, choose the discretization in different fashion here. So you could, depending on the regularity, if this is rough, you could have a smaller H here than here, or you can play with this. We have L2 norm error estimates, and the analysis here follows the fictitious domain argument in each subdomain and Poincaré. But in particular here, of course, you have to work a little bit more with these extension operators because you need extensions both of these bulk domains but also of the trace domains. And then we can do static condensation. So if you do static condensation, then you will want to iterate on the Schur complement. And instead of analyzing the condition number, the condition number here for each subdomain, since it's a fictitious domain method, will be similar as before. But here instead we thought we'd check what is the condition number of the Schur complement. And it turns out to be this. So you get h to the power minus 1, and then you get the minimum over the diameters of these bulk domains to the power minus 1. So you see if these are fixed, then you get, I mean, they are of course fixed in my concept, but you could also think that you reduce the polynomial domains, and then you would get h to the power minus 2, but here we get h to the power minus 1. Okay, so let's see some computational experiments here. So now we have 3 subdomains, and I will consider 2 different cases. The first case is exactly the one I discussed here. I have a global background grid. I'll extract all meshes from that background grid, and I will use Q2 elements. The second approach is an approach where we say, now each mesh is constructed independently. I will have quadrilateral meshes, I'll have triangular meshes, and they will be Q2 or P2, depending on the element geometry. And then on each skeleton subdomain, I will use one Q4 element. So I use high order approximation on the traces. And then, so it looks like this. Here we extract the bulk domains from the global mesh, and we get the 3 submeshes. And you see we get these meshes extracted for the trace. And the other case, I have different meshes. So quadrilateral, quadrilateral, and triangular. And I have these big. So these are like big squares now, because they are, observe that they are not in a lower dimension, these polynomials. We could do that, provided the interface is flat, but I will not go into those details. So this is just to show that we can do something else. Okay, so this is what it looks like. We have right-hand side 1. We have there's a jumping coefficient here, and you see that if you compare these two, they are pretty similar. This is the solution. This is the magnitude of the gradient, and so this matches pretty well. But let's look at the convergence study. So now we have 2 subdomains. We have a known exact solution. We have a jump in the coefficient. This is what the solution looked like, and this is the gradient magnitude. Let's see what this is. This is the case where we have extracted everything from the background grid. Now I have 3 different elements. I have Q1, Q2, or Q3. And this, you see that here we have the optimal convergence orders, and here we have the optimal convergence orders. So this is, of course, just coherent with the analysis. But what about this other case where I have this big Q4 or big polynomial for each skeleton? Well, this is what it looks like. Now I have Q2 elements on each subdomain, and the skeleton subdomains change. So it's always Q2, but here the skeleton subdomain is a Q2. And of course, since the mesh size, the H never changes for the skeleton, of course this must saturate. And then here you have Q4, and then it saturates because it's always Q4 on the skeleton. And this here is a Q6. And here you see the L2 norm. But of course, as long as the skeleton error doesn't dominate, we get the expected convergence order. So what about these more advanced multiscale properties that I thought that we wanted to explore. Well, here now we created these grains by randomly distributing points and creating the Voronoi diagram. And in each cell here, we chose the diffusivity so that it varies between, let's see, what was it? Between 1 and 1,000 in this row-wise fashion. So where it's gray, it's 1, and where it's white, it's 1,000. So you get huge oscillations. But now, since we can choose the meshes differently, the meshes are always aligned with this jumping diffusion. And here we just have a randomly jumping diffusion. So if we compute with the right-hand side, f equals 1, we get this, and here we don't see much, we don't see much of the oscillations, but if you look at the magnitude of the gradient, you see that this captures this oscillating structure. And in the other case, we can discretize. You see here we have a fine mesh, and we have these cells that cut through, and these are Q2 elements, and this is the magnitude of the gradient. Now if we go in this direction, we coarsen the mesh, and you don't see that much change in the solution, but if you look carefully, you can see that the resolution of the gradient magnitude here is getting poorer and poorer. But what's interesting is that, you see, as this mesh becomes coarser, finally you end up with this mesh, where every grain is one polynomial. So this is just a DG method, hybridized DG method. So this then leads to the next part of the talk, because you could think that you could use this as a method, you could have a method on polygonal elements, and then you could have interfaces on the level set variant that cuts through here. So in that case, you might not want to use this simple Nitsche type method, but use something that uses reconstruction to be able to get superconvergence at least away from the interface, or use lower order approximation on the skeleton, but still get optimal convergence. So this is now the last part of this talk, which is hybrid high order method and cut cells. So the hybrid high order method was introduced by Daniele and Alexandre in 2015. And typically you have a mesh, and so I should say that, I'm sorry, this is now a merge of two different presentations, and since the notations in the figures were different, I had to follow that. So now K is the polynomial degree instead of P. Sorry about that. So we have a mesh, we introduce phase unknowns and cell unknowns, and typically in the standard HHO method, if you have K equals 0, then you have piecewise constants on the faces and in the cells, and if you have piecewise linears, you have linears on the faces and in the cells, and then you can get superconvergence using the properties of the reconstruction and the stabilization. We cannot do that in that form here when we have unfitted meshes, so we need to use K equals 0 on the faces and piecewise linears inside the elements. And the discrete problem will be assembled cell-wise. So what is the interest of unfitted meshes here? Well, we have now a method that can be used on very general geometries, but if you have an interface that is curved or cut through these geometries, you might not want to mesh it, in particular if it moves throughout the computation. So it can still give us an advantage to simplify this meshing process. And then fitted hybrid high order methods are not adapted to curvilinear boundaries. So this approach is a very simple way of tackling that and introducing a method where you can have curvilinear boundaries. And as I said, moving interfaces and boundaries can be handled without mesh modification. And so we have a first work with Alexandre on this for the elliptic interface problem. And the key point is that here it is not natural to use this ghost penalty idea. The ghost penalty idea couples different cells and so extends coercivity from one cell from the physical domain, a cell in the physical domain to a cut cell. But I mean, you can do that, but it doesn't seem natural in this context, because you will want to work with cells separately and then do static condensation. So instead, we drew from this work of Johansson and Larsson, where they do agglomeration of cells. So you have to check then if a cell is cut, and if the cut is bad, you'll have to say, okay, now you join your neighbor in a certain fashion. So we have analyzed this also in this paper. There is quite a rich literature on works on discontinuous Galerkin methods with unfitted interfaces, starting from Bastian and Engver in 2009, Massung 2012, and then Johansson and Larsson here. Gurkad and Massing has a recent paper where they do DG and they do discuss a variety of ghost penalty stabilizations. And there's also a related paper that Manolis was mentioning yesterday. Then there's work on hybridized DG and different ideas on unfitted interfaces. There's Coburn, Solano, who are doing these extension techniques. And then there's Gurkan and co-workers who are doing HDG with cut cells. But this is a much more engineering-oriented work than ours. So we are back to our model problem. This is the same as before. We have the cells. They are cut by an interface. Yeah, it's not really the same as before, because before we had jumps over these, like the polygons. But now we have the interface problem, a smooth interface. And well, I have a different notation for the jump here for the same reason. Okay, so now we need to do this separately. So since everything is local here, we need to introduce the uncut cells, what we do in the uncut cells, and then the cut cells. And the uncut cells is exactly what you would do for just standard HHO. So I'll be a bit quicker here. Now here we have the same sketch of the cells with phase unknowns and cell unknowns. In the uncut cells, we can use standard HHO, so we could have constant phase degrees of freedom and constant inside the element as well. Introduce a normal, and we introduce some notation. This U hat combines the cell unknowns and the phase unknowns. The idea is to reconstruct the gradient using this formula that we also saw yesterday, and a stabilization operator. Now I wrote this in this simple form. For the uncut cells, there is a more advanced form that allows you to prove better estimates. But this is what we'll use on the cut cells, so I put it here as well. Okay, so once you have reconstructed, and once you have your stabilization operator, you can define your local operator, this form, and the local right-hand side. And that gives you the uncut cells. This is standard. What about the cut cells? Well, in the cut cells, we have gamma that cuts through, and we need to decompose these cells in a T1 and T2. And we decompose the cut faces, but of course this is a polygonal method, so somehow this is not a problem. We can just say that this is one polygonal face, this is one polygonal face, and there are the others. So they will get their degrees, so they will get separate degrees of freedom. In this fashion, you see I have a degree of freedom here, 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 but also here. But in the spirit of Hansbo and Hansbo, we also double the degree of freedom inside each cell. So here's the cut cell, and here's the uncut cell. So then I need to introduce a T1 and a T2 unknown. But the important thing to observe is that there are no degrees of freedom on this T gamma, the cut here. So then we introduce a reconstruction operator in each of these subcells, which looks the same up to this guy here, which now doesn't couple to a skeletal variable, but couples to its neighbor. And in the paper that we have published, we actually used Nitsche's method inside the element. So you can do that as well. But then we saw that we can actually use HHO everywhere, just that we couple to to the neighbor. And then we need to use this Lehrenfeld-Scherbel stabilization, because it turns out that this projection operator is absolutely essential here to make this work. Okay, and now we have a local operator. Depending on how you choose the reconstruction, this can take different forms. So I wrote it in this form. If I use the simplest form of the reconstruction operator, I need to add these Nitsche type terms in this local operator instead. It turns out that if you play around with this, you can find a G that allows you to get rid of this as well, so that it looks, when you have the local operator, it looks just like standard HHO. But this is not completely finished, so I prefer to keep this form. And then we get the local right-hand side, that will be the source term, and then these terms that will pick up the jumps of the solution or the flux over the interface. And as I said, there are several variants that are possible here. We started and we found this Nitsche type coupling, but actually there's a whole slew of different ways you can couple this with slightly different properties from what you want to do on the local reconstruction stage and what you want to do on this local operator stage. Anyway, those are our operators, and now for the global discretized problem, you get into this situation where you have uncut cells with degrees of freedom here, and you have cut cells with their degrees of freedom here. We introduce a variable for the global set of degrees of freedom, and then we come to this canonical form, where this global H is the sum of the local operators, and this global L is the sum of the local operators. And we want to, then this leads to a big linear system now. And we can still get rid of everything that is inside using static condensation. So somehow this interface condition becomes some kind of submodel here. So I will just be very quick here with the analysis. I will not say much. Yeah, I will say one thing that is interesting. We have this agglomeration. We need a well-resolved interface. And the volume cells will have no bad cuts because of agglomeration, I said. But what does this mean? Well, if you look at this guy here, the white and gray one, you need to be able to inscribe a ball with some kind of uniform radius that is uniform compared to his diameter. But you need to inscribe this on both sides for this to work. So you see, here you can inscribe a ball on this side, but here you cannot squeeze in a ball. So what we do? Well, then we say that this guy, here we can squeeze in the ball, so these two can merge in agglomeration, which is this is the intuitive thought. But what do you do here? Here you can squeeze in a ball, but you can't here. But then he will merge with this guy, which is a bit more surprising because they actually share a node. But actually, if you want to, you can merge this guy with some other neighbor here. They just need to be in an order h distance from each other, because this is all by extension of polynomials between elements. So that's one point. I get now, if I have this cut robust trace inequality, so that will be robust thanks to this agglomeration, then I get coercivity. I have my extension operators like before. I can introduce projections on these sub-cells, and I can prove that they have approximation. In the analysis, I will use L2 projection for this phase. I need L2 projection for the phase approximation, but I never use approximation there. I only use orthogonality or stability, and this is possible thanks to the projection operator in the Lehrenfeld-Scherbel stabilization. Then I get some approximation of this form for the reconstruction. I can prove some consistency, so that if you plug in the discrete error in A, you get this. And this leads to optimal error estimates. I will not say more than that. It's a very similar step as for the standard HHO, just everything goes into the technical details here. So let's just finish and see two computational examples. This is our model situation. And we take a problem with big contrast here. The solution is almost constant outside this circle, and then it has this parabolic profile, so there's a jump, and we only have, so here I only have one, this is first order slope, and this is the first order convergence of the energy error. And here we have a problem with a jump. So you see what the solution looks like here. Both the solution and the gradient jumps. Here we have three different approximation orders. We have first order approximation has optimal convergence, second order approximation has also optimal convergence, and third order has optimal convergence. So this works for these test cases as expected. Okay, I will end there. I've showed you some ideas on how to hybridize cut finite element methods. So if you have a polytopal geometry, you can have an unfitted hybridized method. This requires some stabilization in the interface zone, both for the bulk unknowns and the trace unknowns. So this can indicate the possibility of using a method where you have, if you have local small scale features in the cells, you can resolve that with a mesh. And then if the regularity is higher on the boundary, you can play with this and reduce the coupling between the cells and then get rid of this, the complexity of these small scale features in the linear system by static condensation. And it's also a flexible tool for the coupling of PDEs on the bulk and on the surface. As you can see in this figure here, we have Laplace, the Poisson problem in each bulk subdomain, and then there's Laplace-Beltrami on this line that is then a crack that leads to transport in this direction. So then we had the HH3HHO method with cat elements. So this allows for relatively straightforward discretization of curved boundaries, because if I have a curved boundary, I will just impose the boundary condition without the skeletal unknown, but just using this Nitsche type coupling. I can have interface coupling over interfaces that cut the cell that will then be eliminated through static condensation. So this is in some sense a cell model for interfaces, but it requires cell agglomeration for stability. And we have some all different extensions. So one extension is to Stokes' problem, where you can always do this. So that's all for me. Thank you very much.